Okay, it is already 5 minutes past the hour, so I think we can start if you do not mind. Is it okay with you?
Yeah, sure, definitely.
Okay. Welcome everyone. Thank you for joining us today. IEEE Circuit and Devices chapter is happy to introduce Professor Armin Tajalli lecture today. Let me tell you a small biography about him. Professor Armin Tajalli received his bachelor from Sharif University of Technology, Tehran, and his PhD from Swiss Federal Institute of Technology, Louisiana, Switzerland. He was part of the initiating team and a senior analog architect with Cando Pass, Louisiana, Switzerland, where he is currently the lead of the R&D department. Since December 2017, he joined as an assistant professor to the University of Utah, Salt Lake City, USA. He has published more than 90 articles in peer-reviewed journals and conferences and holds 40 patents. He has received several awards, including the Best Paper Award in DesignCon 2016, PhD Prime Award at EPFL, and IEEE AMD CICC Scholarship 2009. He is currently serving as a technical program committee member at IEEE CICC and European Solid State Circuit Conference, and an associate editor-in-chief for the IEEE transaction on VLSI systems. Please welcome Professor Armin.
Thank you very much for the nice introduction. I'm really glad to have the opportunity to talk about some of our research activities at the University of Utah here in your IEEE chapter. It's a great opportunity for me, and I really appreciate for giving us the chance to come here and present our work. So today I'm going to talk about a fairly fundamental concept, which is about an algorithmic approach to design analog circuits. So it's not about a specific technology or about specific application. It's mostly about how to simplify and get more insight about design of analog circuits. So this is a methodology that for the moment we are just calling it C/ID methodology, and it's based on, as it is clear from the name, it's based on normalization of the parasitic capacitance or self-loading capacitance of transistors with respect to their bias current. And we are going to see how it is going to help in terms of simplifying the design process and finding better design points. So let me see. So today I'm going to start with a very short motivation behind this work, when we started and what was the main reason to start that. We are going to look into some of the existing methods. We are going to see what are the properties or characteristics of each one of those methods. And eventually we, step by step, we move on toward the C/ID methodology foundations, how it can be developed, how it can be used. And eventually I'm going to show you some real results saying that with that insight, with the insight that C/ID methodology gives you, how you can design in a more insightful way your circuits. So the main motivation behind this work was indeed the complexities that we have in the flow of analog design. So this graph that I'm showing here is showing how the complexity of design of analog circuits in comparison to digital circuits affect the profit when it comes to real products in the market. Most of the time, digital design is more systematic, and you have some very robust flows that help you to proceed with design, and eventually the time to market, time to design is going to be much faster than analog circuits. So what does it mean? It means that eventually the profit that company gets from an analog product is going to be delayed. It reaches to the market a bit late. And at the very end, what happens is that the profit will go down. What are the problems? The problems are in different aspects. So the very first step is that automatizing design is very difficult. It's not very trivial. So automatizing design is difficult. There is no systematic way to design all sorts of analog circuits. They don't belong to one family of circuits. We're going to look into that. Of course, everybody is aware that layout is time consuming. Verification is still a lot based on manual work. Scripting is difficult, or at least the existing tools do not support that properly. That eventually results in increasing time to market, right? So, but why analog circuits are important? Here I'm going to give a different perspective about why analog circuits in our today technology are important. It's a slightly different perspective from what most probably you have seen in the past, but it inherently is going to tell you the same thing. So this is a storyline, starts about 100 years ago with Claude Shannon. So he started his master's degree and he wanted to work on, based on request of his supervisor, he wanted to start working on analog computers. But very soon he came back and he said, I found a way to use relays and switches to do Boolean functions. And if you can do Boolean functions, you can implement Boolean functions using hardware, you can implement very, very high-speed calculators. So this became kind of as part of foundations of developing what we know today as digital computers. What is interesting about Shannon's research is that he started as an analog designer. He wanted to exploit analog computers. He moved toward digital design. So he came up with the concept of relays to be used as part of Boolean functions. And he continued investigating other topics like communication, cryptography, coding, and so on. Very, very interesting that circuit design has been part of indeed information technology before anything else. Of course, other people talk the technology part, people like Lilienfeld, and of course, other people started implementing those switches in micrometer scale, trying to realistically implement those Boolean functions. Other group of people try to bring those research work either from theoretical perspective or physical perspective to real products. Right now we have microprocessors in which we have billions of transistors, right? Or analog circuits, which are very, very complex and they do lots of signal processing. And in parallel to that, we have people who have tried to look into the problems that we have in the field of computation from abstract point of view. They have developed Boolean functions, computers based on Boolean functions or digital computers. People are looking into neuromorphic circuits, neural networks, and a lot of other things that indeed are aligned with the roadmap of computing industry. So circuit design is part of computing and information technology industry. Today, there are lots of practical applications out there, wireless communications, wireline communications, sensor interface, and so on and so on. But what really makes analog design still very attractive and interesting is that you could use them to implement very complex computing systems like neural networks, quantum-inspired circuits, health monitoring, right? 5G and 6G systems, bioinformation, and so on. So analog circuit is a very important part of this story of information technology, which could be either computation or communication. So to set the basis and mention why analog design is so complex, you could look into the distribution of different types of analog circuits in terms of their capability to do signal processing. Analog circuits are used to do signal processing. They're not used to do anything else. We are doing some sort of signal processing with analog circuits. This signal processing could be applied to signals which are either continuous in time or discrete in time, or continuous in amplitude or discrete in amplitude. The most common analog circuits that we know or we are aware of that are amplifiers and LNAs and bandgap circuits, which fall into the traditional category of analog circuits, continuous in time and continuous in amplitude. But it is not the boundary of analog circuit design. Analog circuits could do digital discrete time signal processing as well. Switch capacitors have been used for a very long time. And what they do is not continuous time signal processing. What they do this type of circuits are doing a family of signal processing, which is called discrete time signal processing. And of course, they can do also discrete in time and discrete in amplitude signal processing. VCOs, PFTs, and so on are part of that story. Of course, there are a category of circuits which are doing Boolean functions, right? And it turns out that it is very convenient to automatize the flow of design of those circuits, and they are very robust. And we are calling them digital VLSI circuits. What is very important to keep in mind is that the term DSP, that generally we use it as to talk about digital signal processing, indeed includes a bigger family of circuits. DSP sometimes is going to include whatever discrete time signal processing that we are going to do either in analog or digital domain. So this is very important. So we have different categories of circuits, discrete in time or continuous in time, and they are going to have different type of dynamics. So when you are designing them and you are approaching them to optimize their design, most of the time they need different techniques. So now I'm going back and I'm looking into one of the very basic circuit topologies that are used widely in many different applications. And I'm starting with a common source amplifier. It doesn't need to be this one, but the interesting point about common source amplifiers is that although it is considered a very simple circuit, but still there is no clear algorithm to design it. If you come back to me and say, I want to design this circuit and have the minimum power dissipation based on a given spec for a speed, noise, linearity, and so on, most of the time, we go back and we do lots of trial and errors in order to find out where is the optimal point. Of course, this complexity, a good portion of this complexity comes from complexities in device model, right? So a special FinFET transistor or advanced CMOS technology transistors, they are based on very, very complex and nonlinear equations that makes them very difficult to solve everything. The second complexity comes from the fact that design of circuit is very flexible. With two transistors, you could have many, many different topologies and optimize different aspects of your circuit. So all of these items are going to contribute in complexity of circuit design. So where these common source amplifiers are used, just as an example, you could look into different papers, especially in papers which are looking into violent communication, and you immediately realize that this type of circuits are very widely used either to design output drivers on the left-hand side. So, oh, sorry. Let me see how I can go back. Okay. On the left-hand side, I have my, my transmitter, which is using a common source amplifier as an output driver. And on the right-hand side, what I have is the amplifier that I use on the receiver side in order to amplify the signal. Sometimes you have to do some sort of equalization and so on and so on. So what is critically important here is to optimize performance of this circuit, minimize the energy consumption. Everybody knows that in different types of systems that we have, energy consumption or power dissipation is going to play a critical role. So the real question here is that for a given spec, how I'm going to optimize that circuit. So this is the main question that we're going to look into that today. But as a side question, I wanted to take your attention to a second question, which is very fundamental. If you get the chance at the very end, we will talk about that question. Otherwise, we will skip that. The question is that in this wireline link that I'm showing here, I'm using a differential amplifier, both on the transmitter side and on the receiver side. Most of the time, transmitter and receiver, they do two different things. One is doing encoding and the other one is doing decoding. How does it come that we can use this type of analog circuits on both sides? So this is a question in parentheses, so we are going to talk about it at the very end, but I thought it could be interesting for you as well to see, to look into that problem as well. So the key problem that we have today in the field of analog design is that most of the time we start our design based on very simplified models. We do hand analysis, we come up with some sizing specs for the transistor, we put it in a simulator, we design our circuit, and at the very end, when you simulate the circuit, in this circuit is going to use very complex transistor models in order to come up with the performance parameters, right? And these two models are totally different. So this is a problem that was first highlighted by people like Jaspers and Morman. So this is a critical problem, right? There is a big discrepancy between what we do as a designer when we sit behind the desk and what eventually comes back from simulator. We are looking into the problem from two different aspects. We are using very simplified models that are most of the time are not really valid, and simulator is going to use a very precise model. So one approach to solve that problem is to go back and characterize properly those transistors. Of course, it's going to be very difficult to come up with a closed form equation. So most of the time, you're going to collect lots of data in a lookup table, and then you can implement or design or write a MATLAB script such that whenever you come up with a spec, you could make a good search and find out what is the optimal biasing condition for your transistor. What is the best operating point for your transistor? If you do that, then you could bridge between these two bridge a gap, right? In design a step, indeed you can use your lookup table and you could come up with an optimal design. So there are different methodologies that people have proposed. One of the most powerful ones is based on GmID methodology. In GmID methodology, Gm divided by ID is considered as a design parameter, as a design invariant. You could use it, and everything else is going to be described based on that. What you do, you take your transistor and you characterize it for different W values, different L values, for different biasing condition. You characterize and you create a multi-dimensional lookup table, and then when someone comes to you with a spec, you could look into your lookup table and find out which data point, which design point is the optimal point for you, right? The second approach, which is very popular as well, is called inversion coefficient based. In inversion coefficient based approach, what you do, you don't use GmID as a design reference, you use inversion coefficient or inversion coefficient as a design invariant. Inversion coefficient is defined as the bias current of transistor to respect to a specific current. And it turns out that if you use this parameter as your main design variable, you could come up with some analytical methods for characterizing your transistor. You could, for example, use some sort of compact model or EKV model and come up with some expressions that tell you what is the Gm of your transistor or a bias current of your transistor with respect to the size of transistor and biasing condition. This approach is a bit more analytical, but still there are some back and forces between design and spec and different parameters. So what we want to do, we want to base our analysis on those two design methodologies and come up with something that you as a designer can use when you sit behind your desk, right? Something that gives you a bit more insight. You can sit behind your desk, do very, very basic simulations and come up with some basic data and then use it to optimize your design. And not only optimize your design, but also you want to make sure that you get enough insight about design space itself. What happens if I increase or reduce a parameter in my design? Is it going to be okay? Is it going to be not okay? Are there other design parameters or design constraints that I have to take into account? So we want to give more visual view to the designers when they do their work. So to look into this methodology, again, we go back to the most basic circuit topology. We are going to look into common source amplifier, and of course you can apply the same methodology to many different types of circuits. And suppose as a starting point, we want to understand what are the trade-offs in design when you want to reach to a certain gain bandwidth, and your goal is to minimize the power dissipation. How can I do that as a designer without really employing a lookup table or trying to deal with very complex equations that sometimes they don't provide you enough insight? So what we want to optimize is the gain bandwidth of a circuit. And most of the time, gain bandwidth is going to be proportional to transconductance divided by capacitance, the load capacitance that you have. So this is a very, very basic and simple equation. Indeed, it's so basic that it's unbelievable that there is no closed form solution for this problem. So one of the key aspects of this equation, gain bandwidth equation, is that your load capacitance partially comes from the next stage. You could assume that there's something that you know very well. I don't know, you're driving an ADC and you have 100, 200 femtofarad loading from that ADC. And there is a second portion that is because of self-loading of transistor. And indeed, if you look into this equation, this very, very basic and simple equation, you will immediately recognize that the main complexity is because there is no clear relationship between GM and self-loading capacitance. Both of them depend on device dimensions, biasing condition, GM over ID, and lots of other things. Although equation is very simple, but it's very difficult to solve it. Of course, what you could do, you could say my load capacitance is so big that I can ignore self-loading capacitance, right? So I'm going to deal with only self-loading capacitance, and I'm going to be happy if I can just solve that problem. So now again, your equation is going to be simplified to what we see here. Gain bandwidth, which is a given number, is proportional to transconductance divided by 2 pi CL. Again, CL is a given number, so you can clearly estimate and analyze the equation and say what is the GM value that you have. Interestingly, it tells you that what is the GM, but it doesn't tell you what is the bias current. So this is the point that you have to switch the design parameter from GM, which doesn't have any first order indication of bias current, to something which is proportional to bias current. Suppose I define GM over AD as KGM, just to simplify the equations. Now, what I have in my design equation is gain bandwidth, which is proportional to GM over AD times ID, clearly divided by 2C pi. So now I have an indication of bias current. I can move on one step forward, and I say my bias current is going to be 2 pi times gain bandwidth times CL, which is very clear. More gain bandwidth or more loading cap translates into more power dissipation divided by GM over AD. Now GM over AD becomes my design variable. I select the GM over AD and I can tell you immediately what is the right bias current. Just need to tell me what is the gain bandwidth and CL. All of a sudden that complex problem with some simplification turned out to be a very simple problem to solve. I ignored self-loading cap, right? And in the second stage, instead of using GM as a design variable, I use GM over AD as a design variable. So this equation is so simple that I can move on and create a design space for that, right? On x-axis, I have GM over AD as my design variable, and on y-axis, I have my bias current. How much is the bias current that I need to put into my circuit? It's proportional to 2 pi gain bandwidth divided by CL. If you select a bigger GM over AD, your bias current is going to reduce proportional to that, right? What is really, really interesting is that this simplified equation tells you that bias current is proportional to 2 pi gain bandwidth CL, but it's fairly independent of technology, right? If you tell me what is the load that is coming from I don't know, analog to digital converter, and what is the target gain bandwidth, then bias current turns out to be fairly independent of technology. You cannot go below this curve, right? And of course, you can increase the GM over AD, and everybody knows that there is an upper limit for GM over AD at transistor. The upper limit for GM over AD is proportional to 1 over thermal voltage, right? So this is the maximum value. So if you are looking for an optimal design point, probably maximum GM over AD could be a good choice, right? Because you are maximizing GM over AD and bias current is going to get minimized. So up to this point, everything is clear. You don't have any complexity or nonlinear equation in your analysis. You can select GM over AD. Of course, in the next step, you have to find out what is the exact W value, but this is a secondary issue. As a designer, I'm happy that I can see I have such a clear vision on my design space. Now we go back and we bring back what we ignored. It turns out that when you increase GM over AD, it is most of the time it comes with bigger transistor size. You have to increase the W. And if you increase the W, interestingly, what happens is that gradually self-loading cap becomes larger and larger. And at some point it becomes comparable to your load cap, and it increases the bias current. So the optimal design point, which was supposed to be at somewhere in weak inversion, maximum GM over AD, now is pulled back to either medium inversion or a strong inversion, right? And this is the complex part. My simplified equation, just because of load capacitance, now is moved to a point that even we don't exactly know what is the relationship between bias current and VGS of a transistor, right? In medium inversion, of course, you could use some approximate values, but the truth is that we don't know where it is, right? So we don't have now any mechanism to estimate what is the optimal bias current of my transistor. Of course, you could use some trial and error using your simulator. You could go back and forth and you could come up with a couple of design points, but definitely it is very difficult to find what is the theoretical optimal value just based on analysis. Of course, there is a good news, and the good news is that plateau that we have is fairly flat. And if you come up with design point, either the blue one or the green one, still they are going to be very close to the optimal design point. But this is not what I'm looking for. As a designer, I really like to know how this curve looks like. Why I like to know that? Because afterwards, I can combine it with other design constraints like noise and linearity, and analyze my circuits and get some insight. Maybe it gives me some insight about a better circuit topology, right? To me, as a designer, it looks like my bias current is proportional to 2 pi gain bandwidth CL divided by Gm over D. But when my circuit, the gain bandwidth gets closer and closer to the F max of my transistor, this equative breaks down, right? So that's why, as a good guess, as a designer, I added the second term here. This is the term that I'm adding here. I don't really have any clue about that for the moment. I'm adding it to explain what happens when my gain bandwidth gets closer to F max. And unfortunately, as soon as you add this equation, Fmax creates a lot of problems. So one of the problems is that Fmax itself depends on bias current, which means analyzing this equation again becomes very complex. If I could come up with a different definition for Fmax, I could simplify this equation and probably find out what is the optimal design point. So this is a first try from perspective of a designer, not a device engineer, but a design engineer, to explain what is going on in my circuit. So now we are focusing a little bit more on that aspect, and we are trying to find out what's going on exactly in that medium inversion region, how I can really attack and find out what is the optimal value. So to do that, we make a thought experiment. Suppose I have a transistor on the left-hand side, and I'm showing layout of a FinFET transistor on the left-hand side. And this transistor is, this transistor is properly designed. I know what are the parasitic caps and so on. I fit some current, like, I don't know, bias current of IDS. I know what is the W of that transistor, and I know what is the GM or GM over ID of that transistor. I can clearly tell you what is the self-loading cap that I get. If you copy that transistor beta times and create a bigger transistor and multiply the bias current by beta, so of course, bias current will be multiplied with the same factor, W is going to be multiplied by the same factor. Interestingly, GM over ID is not going to change by definition, by construction, right? I have beta times more W, beta times more current, so that's not going to change. But my self-loading capacitance is going to change, unfortunately, right? It's going to be beta times bigger. So now if I carefully look into this equation, I could say, oh, okay, I can define a new parameter, which is self-loading capacitance divided by bias current. And I can tell you that, oh, okay, this self-loading, this normalized self-loading capacitance also doesn't change with scaling the size of transistor. As long as GM over ID doesn't change, CS over ID is not going to change as well. CS over ID, self-loading capacitance divided by ID, is a parameter that is a function of GM over ID, but it is independent of bias current, right? This is the key point. This characteristics cap is a function of KGM, but it is independent of bias current. And all of a sudden, this very, very simple observation will tell me that, oh, let me define this parameter. If I have a characteristics cap, which is defined to be self-loading capacitance divided by IDS divided by bias current, I know that this characteristics cap, this curly C, is independent of bias current. So let me rewrite my equation. My equation tells me that gain bandwidth is proportional to GM divided by C load plus self-loading cap. And I simply replace self-loading cap by characteristics cap times bias current. And now in this equation, I know almost everything, right? My design variable is KGM and my unknown variable is IDS, right? I can move forward and solve the equation, right? I can use the definition of self-loading cap. And now I have a very well-defined closed form equation for my bias current. My bias current, as we expected, is going to be proportional to pi gain bandwidth CL divided by GmID. And it is going to be dependent on self-loading cap, but interestingly, that self-loading cap is not a function of bias current. It's just a function of GmID, right? I know everything about my circuit. The only unknown that I have here is GmID, right? I can clearly explain everything if I just knew what is the self-characteristics capacitance of my transistor, right? So now if I go back to my cartoon, I can explain all portions of my circuit at very low KGM values when self-loading is small, right? This part one of my equation can explain everything. I can explain what's going on at low KGM values when self-loading is negligible. And when self-loading increases, the second part comes into picture and tells me that when you go to higher and higher KGM values, this CGS, this self-loading cap, this characteristic cap, which is a function of KGM, is going to grow. And because of that, you're going to observe some increase in the total power dissipation. Right. So now I have everything. The only thing that I need to extract and characterize is, of course, the characteristics cap, this curly C. So if you go back and look into the bias current versus KGM equation, because the only unknown parameter, the only design variable that you have is KGM, you can't find the optimal point. So the only thing that you need to do, you need to calculate the derivative of bias current with respect to KGM and equate it to 0, right? As soon as you do that, now you get to this equation that tells you the optimal design points for a target gain bandwidth is going to be defined by the derivative of that characteristics cap respect to KGM. And that's all you need. Give me your KGM, I know what is the characteristics cap of my transistor, and I'm going to immediately tell you what is the right operating point for your circuit. And I can analyze it. I can write equations on paper, I can write MATLAB equations and so on, and I have everything. So now IDS versus KGM is something that I can rely on it, right? And this equation tells you that if you want to reach to higher KGM values, this characteristics cap needs to, the increase of characteristics cap with respect to KGM needs to be smaller and smaller. We don't want to jump from GmID of 10 to GmID of 12 and our characteristics cap shoots up. We want to have a very, very shallow slope. As long as we have a shallow slope, we can reach to very high KGM values, very high gain bandwidth values. And this optimal point, this equation that we have here, reveals a couple of very interesting things. So the very first thing is that the optimal design point doesn't depend on your load capacitance. It doesn't matter what is the load that you're driving. The optimal design point, the optimal GmID is not going to change. Of course, bias current is proportional to CL in a linear fashion, but not the optimal point, right? So what does it mean? It means that if you gradually increase your load cap, the optimal design point, the optimal KGM is not going to change. It's going to stay constant. Your curve, the curve that you have between ID versus KGM is going to shift up or down proportional to CL, but the optimal design point is not going to shift, right? So this is one of those very interesting outcomes of this equation. The second thing is that it tells you that the optimal design point is a strong function of temperature. Why? Because the maximum GmID that you can get is proportional to 1 over UT, and it's proportional or thermal voltage, and strongly proportional to temperature. It's going to vary a lot, right? So if you combine variation of load cap and variation of temperature, you will see that the optimal design points might vary over a very fairly wide range, right? So the optimal design points from one corner to the other corner, from one temperature to the other temperature, are going to change. And now you can very precisely, you can estimate how they are going to change with temperature and process corner and CL, right? So everything all of a sudden becomes very clear. The second insight that this analysis provides is that you can generalize the equation to many different circuit topologies. So for example, we did the analysis for a single stage amplifier, right? We did the analysis for that one, but you can expand it and say, if I use, as long as I know what is the exact equality between bias current and GmID, I can go back and optimize any ring topology. It could be a ring oscillator, it could be a frequency divider or latch or D flip-flop. And I can expand it to multi-stage amplifiers. And we're going to look into some examples, how we are going to do that. As long as you can define properly your self-loading capacitance, this approach, this equation, this optimal point, calculating optimal point can be expanded to all those topologies. And we are going to look into some examples. So now the question is, what is this characteristics cap? What exactly, how does it look like? And why the slope of that characteristics cap is so important for us? So this graph here is showing the characteristics cap for a 28 nanometer transistor. Of course, this is calculated for gate source capacitance. So this is the characteristics cap. Then only gate source capacitance is dominant. You can extract similar curves for different types of capacitors. And interestingly, you can analytically explain what is that characteristics cap when you are in strong inversion, right? And of course, when you go to medium inversion, there is no clear equation to describe it. So what we did, we made an attempt to use an empirical equation and explain what is going on in medium inversion. And it turns out that this empirical equation is very, very precise, and you can estimate the characteristics cap in medium inversion and even part of strong inversion, and go back and do your analysis in a very meaningful way. But if you want to calculate it in a more precise way, you just need to take your layout of a standard cell, of a standard unit cell that you have, run a DC simulation and find out how much are the what are the different parasitic caps that you have between gate source, gate drain source, and so on and so on. It gives you a list. Interestingly, W, L, and M, those type of variables are not important. So you can characterize only one transistor, and afterwards, based on scaling, you are going to use it for different dimensions as well. So there is a very simple approach to extract the exact values of your characteristic cap with a very basic simulation. And you can do that post layout, so there is no worry about that one as well. So now how can it help me to move forward and analyze my circuits? So if you have such a very basic, simple means or tool to analyze your circuit, indeed what you could do, you could all of a sudden look into the whole design space. So for example, here what we have tried to do, we have tried to take different transistors, different technology nodes indeed. We have looked into 180 nanometer down to 7 nanometer, because the process of characterization is very, very simple and it can be automatized. We just run a single simulation, which we extract the characteristic cap, and then you could apply the basic equation that you had and find out what are the optimal points. So this graph is showing what happens to power dissipation of your basic analog amplifier when technology scales down. This is something that most of the time digital designers do that very carefully, and they always have some numbers. It might be approximate or it might be precise, but at least they discuss about it a lot. When it comes to analog design, most of the time we don't have, because of complexity of design, we don't have such statistics, right? And now we have everything, because everything has been simplified, boiled down to a very simple equation. So you could look into different gain bandwidth values. So for example, this one is showing 20 gigahertz gain bandwidth, or you could look into 30 gigahertz gain bandwidth and see what happens when technology scales down. For some gain bandwidth values, of course, all technologies cannot really provide you a good solution, but when you go to narrower and narrower channel lengths, you could reach to higher gain bandwidth with lower power dissipation. And you can study which, if you have the flexibility, you can study and see which one of them is the most appropriate for you. As I said, when technology scales down and self-loading capacitance becomes smaller and smaller, at some point, power dissipation is going to saturate. So you can carefully look into that region and say which design parameter is more appropriate for you. So the second example that I have here is a bit more interesting. So suppose you have a certain amount of budget, let's say 1 milliamp budget, and you want to see if you had used different technology node, what is the maximum operating speed that you can reach, right, for a given load capacitance. And you can run your, you can do your analysis, and it turns out that with technology scaling, you can improve, of course, your speed. It's not something very strange, but in 180 nanometer, you might be able to reach only to 21 gigahertz. But when you go to more advanced technology nodes like 7 nanometer, the maximum speed that you can reach for that power budget is going to be 80 gigahertz. It's not linearly proportional to the inversely proportional to channel lengths, but still there is a factor of 4 there. It's not a factor of 20, it's a factor of 4 that can be predicted by this equation, but still it's a good number. And you can look into different technology flavors, high performance, low performance, and so on, and see which one of them could be the most appropriate for you. The other interesting property that this kind of analysis could reveal is that you could apply the design optimization methodology to FinFET transistor and MOSFET transistor and see how they behave. If this time you rearrange your design space based on GmID on the x-axis and look into the maximum gain bandwidth that you can reach, you can see a clear distinction between FinFET transistor behavior and MOSFET transistor. For FinFET transistors, it is much easier to push a transistor into higher GmID values, closer and closer to weak inversion, and still have small self-loading capacitance. This is partially because your gate has a better control on the flow of current inside the channel. So it means your subthreshold slope factor is smaller. And because of that, you have a better GmID factor with less overhead because of self-loading capacitance. So this indicates that FinFET transistors inherently can offer you a more energy efficient implementation when it comes to analog design. Right? The other question that generally people ask, and most of the time the answer is not clear and it comes out based on multiple trial and errors, is that suppose I want to design a very high speed analog front end for my wireless transceiver, and I don't know which topology is the best one. Should I go with a simple resistor based CML stage, current mode logic stage, or shall I use a coil? And if I add coil, how much energy efficiency, how much more energy efficiency I'm going to get? And what happens if I accept the heat in terms of silicon area and I go back and use a T-coil? So each one of these circuits is going to have a different dynamics, right? And it's fairly difficult to analyze them. So when you go from a simple resistor ladder based circuit, if you consider it as a reference, assume that gain is unity and gain bandwidth is unity, consider as unity. When you go to coil based most of the time offers you something between 70 to 80% more bandwidth. You could have some picking or not have some picking. It is going to be slightly different. And when you go to a T-coil based design with maximally flat response, you might get up to 2.83 times more bandwidth. But the main question is not how much more bandwidth I get. The main question is that if I target the same gain bandwidth, what will be the power saving that I can get from these circuits? So now if I go back to the basic analysis in which the optimal design point is going to be proportional to derivative of characteristics cap respect to GmID, and it's going to be proportional to 1/2 pi gain bandwidth, then I can use very, very basic equations. I know that when I go to coil base, I'm going to have 72% more bandwidth. I can apply it here, and I can recalculate the optimal point. And it turns out that if you go from a simple CML-based circuit to a coil-based circuit, you might observe a factor of 2 improvement in power dissipation, right? From 6 units, you go down to 3 units. If you we're targeting a maximally flat design. You could go a factor of 3 if you design a maximum bandwidth, which of course give you some picking and you might like it or not. And eventually, if you go to a maximally flat T-coil base, you can reduce the power dissipation by a factor of 4. And these are the numbers that you can analytically calculate. You can analytically calculate and estimate and put it in your analysis when you do your system design and see which one of them is a better choice for you. So this trend that you see here, by using more and more complex circuits, active passive picking, it gives a lot of design insight as well. So for example, if you look into a T-coil based design, you will see that the design region on the bottom side is fairly flat. So if you like, you could optimize your design for noise. You could go a bit to higher GmID values without losing a lot in terms of power efficiency. Or you could select another design point on the left-hand side, which is more appropriate in terms of linearity. And again, the cost that you pay in terms of energy efficiency is going to be very small. And moreover, you can calculate it analytically. So there is one more question, one more example about multi-stage amplifiers, which is very, very common in design of, for example, wireline transceivers. In front end, you want to know what is the minimum energy consumption that you can get for a given gain bandwidth. And if you do that, you can easily see that with the proper design, you can have at least 30% power saving compared to a conventional design. I don't go to the details because we don't have time, but you can write the equations and look into that. The last example that I have is about a current switching or discrete time amplifier, discrete time current integrating amplifier, which integrates this input signal in time. So what is it offers you some gain, discrete time gain, and also it is very fast. It depends on integration time. So you like to have maximum gain with minimum integration time. And if you combine those variables, you could come up with a very, very similar equation for your bias current. And if you calculate the optimal operating point and compare it with the continuous time amplifier, again, it gives you some analytical solutions which are very, very close to what we know from literature, right? If you are shooting for the same power, if you are using the same power for a discrete time and continuous time amplifier, discrete time can give you 2.36 times more bandwidth. If you are shooting for the same bandwidth, then continuous time amplifier is going to consume 3.3 times more current. Of course, it depends on design conditions and so on, but it offers you a very systematic way to compare the two approaches and select the best one for yourself. What is the next step? I'm going to go through that fairly quickly. So now we have the full visibility on our design trade-offs between bias current and GmID for a given gain bandwidth. We know where is an optimal design point. If you like, you can add noise, and it is very, very trivial to add noise to this design space. Of course, noise is going to change the optimal design point from very, very rare to a new design point, which consumes a little bit more power, but that's fine. This is a new optimal design for my circuit. If you want, you can add linearity as a second constraint and see where is the new optimal KGM value. And of course, this new design point, unfortunately, is not on your curve, on your GmID versus GmID curve, but we know that we can scale up and down the design, I mean the bias current, the power dissipation, by scaling the load capacitance without changing the optimal design points or conditions of my circuit. So I scale up the capacitance, and all of these variables can be calculated in an analytical way, right? So you can develop a very simple methodology to find out what is the eventual final optimal design point for your circuit. So here I'm showing two examples. One of them is on the left-hand side, you have a circuit in which thermal noise is the dominant source of noise. You can see how scaling bias current, how scaling the load capacitance and combining the two helps you to come up and reach this optimal design point. So for example, you might come up and select this design point as optimal power dissipation, and you can analytically calculate what is the theoretical lower limit on your bias current and see how far you are from that data point. Or you can look into a second design in which you have flicker noise as the main source of non-ideality in your circuit and find out what are the optimal design points with different load capacitances. And interestingly, when you look into flicker noise, most of the time people come with points A, B, and C, depending on load capacitance, but it turns out that there are other design points which can offer you better energy efficiency, and you can move to those design points. So I hope I have 2-3 minutes to go through the last stage of my lecture. Going back to the second question that I had, I'm going to make it very, very short. The question was that how does it come that we can use an amplifier both on transmitter side and receiver side, right? On the transmitter side, you expect to have a different function than your receiver side, right? Indeed, on transmitter side, most of the time you encode your data, and on receiver side, you decode them. So how does it come that a differential amplifier can do both of them? If you carefully look into the operation of a transceiver, you will see that on the transmitter side, most of the time you get a single bit, you convert it to differential, you put it on your channel. Now you have on your channel a very good crosstalk rejection and common mode rejection. And on the receiver side, you use a second differential amplifier to convert back your signal to a differential, to a bit, right? You can extract your bit after rejecting the noise. And it turns out that your differential amplifier that can do both of the two tasks, indeed single-ended to differential conversion and differential to single-ended conversion, indeed it has a very basic mathematical model, and that mathematical model can be described by an orthogonal matrix transformation. So this orthogonal transformation that takes the bit, converts it to a differential value, and again converts back that differential value to single-ended value. This orthogonal transformation indeed is a very well-known transformation. People are using it in communication a lot. And the nice properties of this transformation are the things that can explain why your differential signaling system is robust against common mode noise and crosstalk and so on. This transformation is very well known. It's known as Hadamard transformation. And the main problem with this transformation is that most of the time you need 2 wires in order to send 1 bit and maintain good resistivity against crosstalk. If you like, you could go to Hadamard, a higher order Hadamard transformation, and improve your throughput by 50% and even more, and maintain the nice properties in terms of crosstalk cancellation and so on. Take binary bits on the transmitter side, put them on the wire, and again on the receiver side, you can decode them and hand over binary bits to your slicer. And this very, very basic, simple observation helps you to implement a link, which is very robust against inter-symbol interference, and at the same time very robust against crosstalk. So in summary, what I wanted to say today was that analog circuits are key portions of today's communication and computing industry. Unfortunately, because of complexities in design, time to market is very long, and there are lots of problems in this path. So we need, as analog designers, we need to come up with better approaches to solve that problem. And the very final point that I wanted to highlight is that analog designers in modern industry, not only they need to know how to optimally design their circuits, but also they need to know a bit more about other skills, like how to come up with good coding and signaling schemes in order to improve performance of their circuits and come up with more energy efficient implementations. I hope I didn't go that much above the budget that I had. So I'm sorry, the mouse doesn't work. And I really appreciate your patience. Thank you very much.
Thank you, Professor Armin. Thank you so much. The talk was very interesting. I think we still have enough time for a couple of questions. If anyone of the audience have any question, please feel free to write it in a message or to unmute yourself and ask any questions that you would like.
Yeah, great.
Hi, Armin. This is Peter Levine from University of Waterloo. Yeah, I really enjoyed your talk. Just had a question about the variable you introduced, the curly CS. I was wondering if you could just review how you or how you define that, and where you introduce that. I just didn't catch that.
Yeah. So this slide kind of shows why curly C is important. Curly C, which is by definition, is you simply take your self-loading cap, suppose gate drain cap, and you divide it by bias current. This slide tries to tell you that this simple operation, dividing gate source cap or whatever by current consumption, makes it independent of bias current, right? If you maintain the GmID, right? When you go from left-hand side to right-hand side, if you make your size of your transistor, for example, 2 times bigger, and you put 2 times more current, and you increase the W by a factor of 2, GmID doesn't change, right? And self-loading by definition is going to be multiplied by 2. What does it mean? It means that if you divide self-loading by bias current, you are now creating a parameter, a new variable, which is independent of bias current. Curly C is a function of GmID, but it is independent of bias current. And as soon as it becomes independent of bias current, I can take it and I can put it in my equation, right? And the nominator side, what I have, this one is simply Gm, right? And on the denominator side, what I have, this is my self-loading cap. Now I replace it with bias current times this curly C. And I know that curly C is independent of bias current. If it is independent of bias current, I can reorder the equation and come up with a very explicit way of calculating bias current. My bias current becomes 2 pi gain bandwidth times CL, this is what I knew, divided by KGM, minus a second factor that, again, I was guessing that this is something dependent on self-loading, and it turns out to be 2 pi gain bandwidth curly C, right? Interestingly, this curly C is independent of bias current. So this equation now is solved. As long as I know what is the relationship between curly C and KGM, I know everything.
Okay. Yeah, okay. Yeah, thank you. And just to follow up, is it possible to reformulate these equations and instead of using GM over ID to use current density, ID over W?
I think so. Even if you look into inversion coefficient methodology, they're using a parameter which they call it CW. And what they do, they divide the C by W. Indeed, they make a very smart choice, but this smart choice is not enough to give them the flexibility to solve the whole equation. So I think you can use GM over ID as a variable, or you could use GM over W as an independent variable. This should be doable. Okay. We haven't tried, but you should be able to do that.
So GM over W, but ID over W is not.
Oh, sorry, ID over W.
Oh, so you would, because I tend to use that as opposed to GmID, but yeah, that's something I'd like to see. Okay, yeah, thank you.
The good point about curly C or C over ID is that all of a sudden you have an equation, and as an analog designer, most of the time we like to have the equation. We want to fill it and plot it and find what is the best optimal choice for us.
Yeah. Yeah, great. Yeah, thanks.
Sure. We have one more question here in chat. It's saying, can you show how to extract the CS in simulation?
Yeah. So indeed, it is fairly trivial. So you take a transistor like this one. You take a transistor. It could be post-layout extracted transistor. And what you do, you select an arbitrary size. Interestingly, size is not a critical factor. You can, for example, select M to be 10, W to be, I don't know, 2 micron, and so on. And you fix it on your test bench. And what you do, this amplifier here is just to make sure that your transistor doesn't go into triode region. So you apply a drain source voltage, which is slightly larger than your saturation voltage. Otherwise, you don't need that amplifier in it. And what you do, you sweep the bias current. You sweep the bias current from, I don't know, 10 nanoampere to 10 milliampere, right? What happens is that when you do that sweep with a fixed size transistor, your GM is going to vary. Indeed, your GM over ID is going to vary. So what you get as an output is GM over ID and self-loading cap divided by ID. Indeed, ID is something that you know. You just simply divide the parasitic cap by ID, and that's all. That's done. You have your curly C. And the nice thing is that you can do that post layout. Most of the time for other approaches, if you want to change W and L and so on post layout, you need to have layout for each one of those individual cells. Here, you do that only for one basic cell, whatever you have.
Great, thank you so much.
Yeah,
I think we can still have one more question if you don't mind. If anyone still have a question, feel free to chat or to unmute yourself.
Maybe while we are waiting, I add a quick comment to what I mentioned.
Sure.
If you have in your schematic, if you have some self-loading cap, you divide it by bias current and it gives you the curly C, the characteristics cap. In layout, if you add some parasitic cap, what it's going to do, it is going to increase the value of your characteristics cap. And if you're shooting for a given gain bandwidth, right, you have to calculate the derivative of this one with respect to KGM, right, and equate it by 1/2 pi gain bandwidth. What does it mean? It means that if parasitic cap, as an example, is your parasitic cap is as big as your self-loading cap post layout, what does it mean? It means that for the same biasing condition, your gain bandwidth is going to reduce by a factor of 2, right? This equation immediately implies that. And it can tell you what is the new optimal point. Very, very trivial, very, very simple.
Thank you so much for this additional information. I think we didn't get any more questions, so I think that's it for today. If no one else want to ask any more question, I will stop recording right now.